All right, so this video is for AP Stats. If you're in period 5, this is the only video you're watching today. If you're in period 6, this is the second video that you're watching today. This one will be pretty short. We're not going to do the whole handout. Just a couple of things real quick. On the handout that says standard deviation is a ruler, part 4 of 4. And we're actually going to start with how about we start with tomatoes? Let's start with tomatoes. It's like at the very end, problem 48. Roma tomatoes. Okay, so when we read this problem, it says, agricultural sciences. Reading backwards. Okay, I better read it for here. This is easier. Agricultural scientists are working on developing an improved variety of Roma tomatoes. Marketing research indicates that customers are likely to bypass Romas that weigh less than 70 grams. Okay, so that's the standard. They've got to weigh, these tomatoes have got to weigh at least 70 grams. Now, the current variety of Roma plants produces fruit that averages 74 grams, but 11% of the tomatoes are too small. It is reasonable to assume that a normal model applies. So, what is the standard deviation of the weights of Romas now being grown? You see, when we've used our mechanics formula, z equals x minus mu over sigma, sometimes we've solved for z. In the previous lesson, we solved for x. This is the first time that we're going to use the mechanics formula for z to solve for sigma. It's a new algebraic task that lies before us. So, in order to wrap our minds around it, let's draw the bell curve. Okay. We want the current variety of Roma plants produces fruit that averages 74. So the model that we'll use will be a normal model with a mean of 74. Notice the standard deviation is unknown. They're not telling us the standard deviation, but we know the middle is right here, 74. And we know that the cutoff for too small is 70 grams. These are, the title here is Roma tomato. I'll abbreviate, no abbreviations. Tomato weights. Okay, here we go. 70%, 11% are too small. So go ahead and shade the bell curve to the left of 70, which is the cutoff between too small and not too small. And since we're told that 11% are too small, let's arrow 0.11 to the shaded region. And, oh, it's not showing up. It's not showing up. There it is. 0.11 Roma tomato weights. So we have 3 of the 4 numbers in the bell curve. We need the 4th number, and we get it from the mechanics formula. So here we go. Z, let's see, 74 grams. Okay. So what's the standard deviation? So let's find out what the corresponding z-score is for 70, and inverse normal can do that. Would you think about what number goes into inverse normal to find the z-score that corresponds to the cutoff value of 70 grams? And left area. I hope that your conclusion is that the left area for the cutoff at 70 grams is 0.11. So inverse normal at 0.11 gives me negative 1.227. So I'm just going to put that up here. Z equals negative 1.227. And just to document my work here, that came from, in purple, inverse normal of the left area, 0.11. That actually gave me the z on the right. So now I can go to mechanics and solve for sigma. And z gets replaced with negative 1.227 X is the cutoff of 70, the mean is 74, sigma is unknown. So you remember back in algebra, you solve things like this. Negative 1.227. We simplify 70 minus 74 to get negative 4 divided by sigma. And I'm going to multiply both sides of this equation by sigma. When I accomplish that, the sigma cancels on the right. We get negative 1.227 sigma equals negative 4. All that remains is to divide both sides by negative 1.227. The negatives cancel, giving me 4 over 1.227. So on the calculator, let's type that in. 4 divided by, basically this number. Actually, let's take negative 4 divided by answer, which should be the same thing as 4 divided by 1.227, although since I rounded this, it'll be a little bit different. It's basically about 3.25. So our standard deviation is in grams, approximately 3.26 grams. So conclusion, according to the normal model, the standard deviation of the weights of Roma tomatoes, we're writing in context, now being grown is 3.26 grams. If someone asked you to interpret the 3.26 grams, you should be able to look at that and say, well, 3.26 grams is the typical difference between a particular Roma tomato's weight and 74 grams, which is the mean Roma tomato weight. That's what we mean by 3.26 grams. The typical difference between a particular Roma tomato and the mean weight of a Roma tomato. Moving on, part B. This time we're going to have the new experience of using the mechanics formula for Z. Instead of solving for sigma, this time we're going to solve for mu. We've never solved for mu before, but today's the day. Today's the first day we solve for mu in the Z-score formula. All right, this is dead. What's going on? Scientists are hoping to reduce the frequency of undersized tomatoes. They don't like 11% undersized. Too many get thrown away. We want to change it from 11% to only 4% that are too small. And so the strategy is going to be to take the bell curve and shift it to the right. And just to make this somewhat dramatic for you and dynamic, okay, so it will be a lot of drama, but there will be some dynamism going on here. So we're saying that the old way of doing things had 11% tomatoes that are too small. So as you can see, 70 used to take, it had too many thrown away. The shaded area corresponds to the amount thrown away. So the strategy here is we want to make these things bigger, maybe through genetic engineering or something scary, just as scary as that. And so we're going to say, instead of the mean, oh yeah, I should give you the blue mean. So the mean used to be 74. And we were throwing away 11% because they were too small. Now we're going to say, let's make them bigger on average. And if we make the tomatoes bigger on average, so that's 74, and now it's up to mu, then only 4%. Notice how when you increase the mean size of the tomato, the percent that are under 70 grams shrinks from 11% down to 4%. So the question is, what is this new mu? What's the new mu? Not the new you, the new mu. So to figure this out, let's see, we've got, oh, yeah, they didn't tell us that Z, it's there. Is that there on your paper? So anyway, to find out the Z-score, which happens to be negative 1.751, in case it's not on your paper, what you would be drawing is, now I'm really curious. I'm going to see if you have it on your paper. I'm back. Okay, so you do have that on your paper, which makes sense. In case you're wondering, where did they get the negative 1.751? Well, of course, that came from, in purple, inverse normal of the left area 0.04. And you can confirm that on your calculator, that distribution inverse normal 0.04 is in fact negative 1.751, so that's where it came from. So notice how the mechanics formula works. Z equals x minus mu over sigma. We just found the Z-score. In purple, negative 1.751. We know the cutoff. 70 is the cutoff for tomatoes that are too small. We don't know the mu value, but the sigma comes from the previous problem. If the standard deviation remains the same. So this model here is the normal model, unknown mu, but sigma is the same as what we found up here, which is 3.26. So we use the answer from part A to work part B. Put a 3.26 here. I want to see if you remember how to solve equations for a variable. I'm going to turn off the camera. You can go ahead and solve for mu, and then we'll come back and talk about it. So pause it, please. All right, let's see how you did. We're going to multiply by 3.26. And if I take negative 1.751, do I have that here? Yep. If I take the Z-score and multiply it by 3.26 times 3.26, I get negative 5.707. Let me just write that down. Negative 5.707. There's some rounding here, but we allow for that, equals 70 minus mu. Next, I'm going to subtract 70 from both sides. On the calculator, that's not too tough, because all we have to do is press minus 70. We're up to negative 75.707. So negative 75.707 equals negative mu. Multiply both sides by negative 1 to get 75.707. So there it is. We should do something to these tomatoes so that instead of the mean being 74, the mean should now be 75.7. So according to the normal model, the target mean, the average weight for the tomatoes, the Roma tomatoes, should be 75.707 grams, or basically about, you know what, let's shoot for 76, shall we? Let's just play it safe. We're going to do all this work to genetically engineer these things so they're bigger, or do something to make them bigger. Let's get them up to 75.7, or about 76 grams. 76 grams, then we will have achieved our goal of having only a 4% too small rate. Let's go to the next page. And, okay. And now the researchers produce a new variety with a mean weight of 75 grams. Are they trying to build off the previous problem? I guess maybe that's what we're doing. So it was, I mean, we rounded up. So maybe they decided to go with 75 instead of 76, which is fine, I guess. And that meets the 4% goal. What's the standard deviation of the weights? Oh, you know, this is just it's a separate problem. This is just like new givens. They're just announcing to you that they did a new variety through genetic engineering, apparently, where the mean is 75. We don't know sigma, and it does meet the 4% goal. So what's the standard deviation? That's a review problem. We're just doing Z equals x minus mu over sigma with a Z-score of inverse normal of 0.04 is going to give you negative 1.751, just like before. X is 70, mu is 75. They just told us that. Solve that for sigma. So if you do the math and solve that for sigma, you will get body temperatures in tomatoes. you will get standard deviation of 2.856. My phone. Okay, we're going to pause. I take my phone call. Pardon back. So the standard deviation on that one came out to be 2.856. And in part D, it says, based on the standard deviations, compare the tomatoes produced by the two varieties. So the idea here is that the weights of the new tomatoes have a lower standard deviation than the weights of the current variety. The newer tomatoes have more consistent weights. So the smaller standard deviation in the real world, what that means is that there's less spread on the weights. So the weights of this new variety is just more consistent. There's less variation. So the homework, remember the homework that's due on Monday is homework 2.1. And that has to do with, you know what? We might want to do one more practice problem on that. Just hang tight. Yeah, I just realized part F has an absolute value in it. So let's do one that has absolute value to make sure you're good to go with that. So let's do one similar to part F. Let's just do it right here. Suppose you had to find, we can call this problem like part F. So we're going to say the probability that the absolute value of a standard score being greater than C is equal to, let's say, 0.614. Okay, so we need to set up a bell curve that this is not happening. So we're going to put that back where it belongs. Select, lock. Hello, we're back. So let's select this without selecting the underlined text and set up a picture of what it means for the absolute value being greater than C to be equal to a number. So the absolute value being greater than C, if you had a situation where the absolute value of a number was greater than 5, suppose C was equal to 5, what would that mean? That means that the distance from 0 is greater than 5. So any values on the number line that are greater than 5, or any values that are less than -5 would be considered numbers. These shaded values are numbers whose absolute value is greater than 5. You probably remember that from studying absolute value back in Algebra 1. So if the absolute value of Z is greater than 5, means all the numbers greater than 5 and all the numbers less than -5, then the absolute value of Z being greater than C means here's 0. We're talking about all the Z scores greater than C and less than -C. So this is your picture for finding the probability. We have to find the area of these two shaded regions combined. And to do that, we have to realize that the 0.614 is found by taking the right shaded region plus the left shaded region. So if I want to find out what -C is, I mean, that's a left area. It sure would be nice to know what this left area is so I could do inverse normal of left area. Well, by symmetry, each one of these shaded regions is half of 0.614. And half of 0.614 is 0.307. So this tail is 0.307. And that tail is 0.307. So I think we can find -C by doing inverse normal of the left area, which is now revealed to be 0.307. So here we go. Inverse normal of 0.307 is -0.5044. So let's fill that in. -0.5044. And this would be positive. By symmetry, this would be positive. I don't even have to go with the calculator. 0.5044. Therefore, the answer is C is approximately 0.5044. There you have it. That concludes the lesson. Assignment 2.1 is due on Monday. Have a good weekend. If you haven't read chapter 6, read chapter 6. Bye.